A solid sphere and a spherical shell roll down without slipping on an inclined plane. They have same mass and same radius. They both start from rest. We're asked to find the ratio of their angular velocities as they reach the horizontal level. Okay, so what we will do here is we will try to find the angular velocity for a general round body, and then we can use the moment of inertias to answer this question. Okay, for a spherical shell, what is the moment of inertia of a spherical shell if it is getting rotated about the center of mass axis? Okay, so these are few things that we should all know, and I'm assuming you know. For a spherical shell, if m is the mass and r is the radius, the moment of inertia about an axis passing through its center of mass is 2 by 3 mr square. And if you get it for solid cylinder, okay, so it is mr square by 2. So we are going to use these values. Okay, now let's take a look at the diagram and then see what is going on. Okay, so you have a round object here. So this can be solid cylinder or the spherical shell. It starts from rest at a certain height. Okay, so we're going to take the center to center distance here. Okay, so center to center distance, let's consider that as h. Okay, so this distance is h. Okay, and once it comes to the horizontal level, it has some angular velocity and also center of mass velocity. Okay, and we are interested in the angular velocity. Okay, the objects start from rest at a height h. Okay, now in rolling without slipping, okay, the points of contacts, they don't really slip on the ground. Okay, so there is no loss in mechanical energy. So here in these problems where they specify that the object is rolling without slipping, we can simply go ahead and then use conservation of mechanical energy. So here clearly the height has reduced, so there is a loss in gravitational potential energy. So the potential energy lost is equal to kinetic energy gained. Okay, so what is the loss in the potential energy? It is mgh. And what is the gain in the kinetic energy? So here you have to be careful. We have two kinds of kinetic energies. We have translational kinetic energy, which is half mv square, and we have rotational kinetic energy, which is half I omega square. So here I is about a center of mass axis. Okay, so the axis passes through the center of the solid cylinder or the spherical shell. Now we are not interested in V, but we know that pure rolling, the points of contacts don't slip. So magnitude wise, the center of mass velocity is equal to r times omega. Okay, so is equal to tangential velocity of a point on the periphery of the object. Okay, so we can substitute v here. Okay, so we have half m, v is r omega, so we have r square omega square plus half I omega square. Okay, and then what do we have here? So if I take omega square, so this is mgh. Okay, I can take omega square common, and I can write omega square as 2 mgh divided by I plus mr square. Okay, I plus mr square. Okay, so if I need omega, I just have to now take a square root. Okay, so omega is square root of 2 mgh by I plus mr square. Okay, I think we have the required expression. Now we just have to substitute the moments of inertias and then get the required ratio. So we need angular velocity of spherical shell to that of the cylinder. Okay, so angular velocity of the shell divided by angular velocity of the cylinder. Okay, so now I think when you are taking the ratio here, it's okay to ignore a lot of terms here. Okay, so capital MGH and then 2, so they are common for both of them. So here I think I'm sure you'll follow here. So for the shell, if I ignore these quantities, okay, so I'm going to ignore 2 mgh. Okay, so there is no point writing down because I'll be writing for the shell as well as the cylinder, and then they are going to get cancelled anyway. Okay, so we'll not write them. Okay, and then for the shell, what do we have? I of the shell plus mr square, and for the cylinder it is I of the cylinder, okay, plus mr square. So you understand why for the cylinder I have written in the numerator, and shell corresponding expression I have written in the denominator. Okay, so of course don't forget to take the square root there. Okay, so I think we are almost there. Okay, so what is the moment of inertia for a cylinder? It is mr square by 2. So let's substitute that. Square root of mr square by 2 plus mr square divided by, for shell it is 2 by 3 mr square. So I have 2/3 mr square plus mr square. Okay, so here you can see that everywhere you have mr square. Okay, so you can ignore that and then just pay attention to the numbers there. So what do we have in the numerator? 1 by 2 plus 1. Okay, so you have 1 by 2 plus 1, so that's 3 by 2, and here 2 by 3 plus 1. I don't want to go to next page. Okay, 2 by 3 plus 1, that's 5 by 3. Okay, so I think this gives us 9 by 10. So we can write square root of 9 is 3, and then 3 by square root of 10. So if you look at the question, they are saying, okay, the ratio is written as 3 by square root of x, and then we are asked to find x. So clearly x is root 10. Sorry, x is 10, not root 10. So x is under the square root, so x is 10.